Hello everyone. Today we'll be going over autoencoders. We'll do this in parts. So this is the first video, kind of an overview of what's going to be going on here. We'll dive deeper into the math and the model architecture in future videos. So we have these things called autoencoders. Okay. The simplest version of an autoencoder does this. All right. The idea is we want to learn what is called a latent space or a latent representation. Okay. What does that mean? I'll give you an example. Okay. Let's say that we're trying to learn how to draw images of circles. So I'm going to draw three. Let's say this is like my canvas, right? Three blank canvases. And this is one circle, and this is the other circle, and this is the third circle. So remember, these are all images, right? So let's say an image is 224 pixels by 224 pixels. So that's 224 squared pixels, right? That's high dimensionality data. That's a lot of dimensions, right? So one way I could tell you how to draw this circle would be, okay, at each pixel, pixel, this is the color value I want. So in the first pixel, which you can imagine this broken up into small pixels, at the first one I want 0 color, at the second I want 0 color, third 0 color, fourth, etc., etc., etc. And then maybe at this random one I want you to put a dot or something. And you'd be like, wow, that's very useless, right? That's very complicated for no reason, right? Is there a better way we can represent the idea of drawing a circle? And there is, right? So instead of being in whatever R224 squared in the 224 squared dimension world, we can represent this in R2. And the two dimensions I would give you would be the center, and I would give you a radius, right? Now, if I give you a center and a radius, you don't need this high dimension to describe this circle. You can do it with a much more compact, latent representation, okay? So in general, what we're doing with autoencoders is in comes some high dimensional data X. Okay? We feed it to the autoencoder. This part is called the encoding step. So this is an encoder. It will take your high dimension X and learn a latent representation Z. Okay? Then obviously we have an encoder, so we need some way to now take this Z and produce back out, right? Using a decoder, we're going to produce back out an X hat, okay? And the idea is you want to learn an encoder and decoder network that are learned with neural nets that can take this input X. So let's say this input is 1, 2, 3, 7, 8, 9, whatever, 251. This input is 251 dimensional, right? We learn a smaller, more compact representation of it, maybe 4 dimensions, right? And then let's say this original input meant something, like the image of a cat or something. Then we learn a decoder that can take the specific Z for this X and decode it and return back an image of a cat. Okay? The way these are usually trained is that, again, if your, let's say your input X was an image, right? So image, let's for simplicity just make it broken up into, let's say the image was only 9 pixels, right? Then your output X is also going to be an image, 9 pixels. Remember, in vector form, these would just be a vector of 9 numbers, but you could take something like the mean squared error. So you could say, okay, this is my first pixel here. So let's label these 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So these would be your labels for the pixels. And you could do like pixel 1, right? Minus pixel 1 from the reconstructed, minus pixel 1 from the original, squared, plus pixel 2, etc., right? And you could basically find, this is a very simple model that, the error is just the difference between the two. And so you optimize using gradient descent, and you learn the weights in your network to make this encoder learn an efficient and compact representation, and this decoder be able to take that compact representation and output the original image. Okay, now these are good for a lot of things. One thing that you can immediately see is that this is great for compression, right? If we can efficiently learn this encoder-decoder network, then we don't have to store these huge dimensional vectors. We can store the smaller ones because we know that we can always decode back to a good representation of our original vector or image or whatever. Okay. The other thing is this is good for learning features. For example, right, when we learn the latent space, we're saying that really these are the numbers that actually matter, right? Your other stuff here, yeah, it was important, but at the end of the day, when you're just looking to reconstruct to a certain level, you don't need all of this extra dimensionality. These are the important features. So that's another thing that autoencoders can be used for. Now, there is an issue with autoencoders, which is this fact. So let's think about kind of let me draw a diagram here. So here is my high dimensional world. Okay, so this is a high dimensional world, and here's my low dimensional world, aka my latent space. So this is my latent space. Okay, whatever the dimensions may be. I mean, I'm obviously drawing it on 2D, but these are any dimensions, as long as this one is smaller than this. So let's say we're using an autoencoder for images of animals. So I take a cat. This right here is an image of a cat, okay, in high dimensional. It gets mapped to some point in the latent space, okay? Then I have an image of a dog, right? And that dog gets mapped to some point in the latent space. Then I have, I don't know, a cow, right? And that gets mapped to some image in the point in the latent space. So now, if I want to reconstruct, so basically I have, my cat here gets mapped to a cat here, right? Or whatever. If I want to reconstruct my cat, I can pass this specific latent representation through the decoder. So this is the encoding step, right? Going from high dimensions to low dimensions. I can pass this through a decoder and get the reconstructed output. All good. The issue is that if I pick any other point in the latent space that hasn't been chosen already, then the representation that if I take, if I take this exact cat picture and decode it, I should get out a nice image of a cat. In fact, the exact same image of the cat that, or as close as possible as we put in the first place, right? Same thing with the cow and the dog. But if I choose a random point here, the output will be nonsense. It won't be an animal, it won't make any sense, because we have only learned the latent representations for these specific points and exactly their specific points. Okay? We don't learn the entire latent space as a whole. We learn only the points, the data that we're inputting, which is good because we can at least accurately reconstruct those. That's also bad, right? We want to be able to maybe work with this latent space, try and generate new images, right? We want to, maybe if this is where, cats get sent to, maybe if I sample a point right here and I decode that, maybe that should turn into a different type of cat or a new image, okay? So this is where we get into the idea of variational autoencoders. So variational autoencoders. Okay, and for that, I think this video is already getting long, so I'll touch on that I'll start with those in the next video.